The Earth's climate is governed by its energy budget, a delicate balance between incoming solar radiation and the heat that escapes back into space. This balance is not static. It is constantly shifted by natural orbital cycles, tectonic movements, and, in the modern era, significantly altered by human activity. Greenhouse gases like carbon dioxide and methane act as a thermal blanket for our planet. By trapping outgoing infrared radiation, they regulate the planet's temperature. This process is fundamental to the natural climate. However, modern human activity is increasing these gas levels, thickening this blanket and driving global warming. Volcanoes are dual actors in Earth's climate system. Over long geological timescales, the continuous release of carbon dioxide from volcanic activity contributes to a greenhouse effect, gradually warming the planet. Conversely, massive explosive eruptions inject sulfur aerosols into the stratosphere. These particles act as a reflective shield, increasing Earth's albedo and causing temporary yet significant global cooling. The net impact of volcanic forcing depends on the frequency and magnitude of these events, balancing the warming influence of carbon against the cooling shadow of aerosol layers. As of mid-2026, scientific consensus confirms we have moved from a climate governed by natural forcing to one dominated by human-induced change, primarily through fossil fuel emissions. Historical data reveals that atmospheric carbon dioxide levels remained within a stable natural range for 800,000 years. The modern era shows a dramatic, rapid departure from this baseline. The overwhelming scientific consensus confirms that human activities are the primary driver. We are tracking this shift through natural records, which show that recent temperature increases correlate directly with anthropogenic emissions. For 800,000 years, atmospheric CO2 levels followed natural rhythmic cycles, consistently staying below 300 parts per million. However, the industrial era has shattered this historical norm, resulting in a vertical spike that defies geological precedent. As of 2026, global CO2 concentrations have breached the 425 to 430 parts per million range. This threshold acts as a primary engine for the current acceleration of global surface temperatures. Albedo is a measure of how much solar radiation a surface reflects. On a scale of 0 to 1, surfaces like snow have high albedo, reflecting most light, while dark surfaces like asphalt have low albedo. When solar radiation hits white ice, it is mostly reflected back into space. In contrast, dark ocean water absorbs this energy, converting it into heat. This creates a self-reinforcing loop. Rising temperatures melt Arctic sea ice. This exposes dark ocean water, which absorbs more solar heat. Consequently, temperatures rise even faster, accelerating the melting process. Satellite observations confirm the significant reduction in sea ice concentration over recent decades. This loss of reflective surface is a primary driver in the acceleration of global warming. The Atlantic Meridional Overturning Circulation, or AMOC, is a vital system of ocean currents that transports warm surface water toward the North Atlantic. Recent observations show the AMOC is weakening. A primary driver is the influx of fresh water from melting glaciers in Greenland, which reduces surface water density and disrupts the circulation flow. This disruption creates a paradoxical effect. As the conveyor slows, northern Europe may experience localized cooling, while heat builds up significantly in tropical regions. Scientists warn that we are approaching a tipping point. Once surpassed, these circulation changes may become irreversible, drastically altering the global climate balance. The Earth operates as a complex dynamical system. We are currently facing a critical fork in the road, transitioning from a stable climate into a potential hothouse phase. Feedback loops are the drivers of these tipping points. A positive feedback loop acts as an amplifier, where an initial change, like melting ice, reduces surface reflectivity and accelerates further warming. A clear example is permafrost thaw. As global temperatures rise, frozen ground thaws, exposing ancient organic matter to decay. This releases methane and CO2, which further increases temperature, creating a runaway cycle. Once these threshold limits are surpassed, the Earth's climate system shifts into a new state. Because these feedback loops are self-sustaining, reversing their effects becomes one of the greatest challenges of the Anthropocene. The human impact on Earth's atmosphere is now so distinct in isotopic carbon ratios that scientists are formally refining the Anthropocene as a specific geological epoch. This chart shows how this new era distinguishes itself from the Quaternary period, with 1950 serving as the formal boundary. The primary evidence lies in the inverse relationship between atmospheric carbon dioxide and the carbon-13 isotope ratio. When we burn fossil fuels, we release carbon that has been sequestered for millions of years, which is chemically depleted in carbon-13. This creates a specific isotopic signature that acts as a human fingerprint in the atmosphere. These signatures are now being locked into Earth's stratigraphic layers. Future geologists will find this distinct chemical transition in the rock record, marking the undeniable moment when human activity became the dominant driver of global climate change. Climate change is rarely a gradual, steady process. It is characterized by nonlinear shifts where the system remains stable until it reaches a critical threshold, leading to an abrupt transition. The tipping point effect illustrates this phenomenon. Once the system crosses the 1.5 degrees Celsius threshold, it moves from an uphill struggle to a downhill, self-reinforcing state. Mathematically, this appears as a bifurcation. As climate parameters increase, a single stable state may branch into multiple complex outcomes, representing a jump to an entirely new climate state. Once these thresholds are crossed, the climate system enters a new state that is rarely reversible, necessitating a focus on preventing these dangerous transitions. Radiative forcing measures the energy imbalance in Earth's climate system, essentially the difference between incoming sunlight and outgoing heat. This chart breaks down the forcing drivers relative to 1750. Notice how the total anthropogenic contribution has grown significantly over the last several decades. Today, human-induced radiative forcing is over 3 watts per square meter. This signal is statistically far greater than the impact of natural solar cycles since 1950. While solar variation fluctuates, its impact on the energy budget is negligible compared to the rapid increase in greenhouse gas concentrations. Sea levels have been rising throughout the modern era, but the rate of this increase is changing significantly. Over the last 2 decades, the rate of sea level rise has doubled compared to the 20th century average. Models now project a potential increase of 0.5 to 1.0 meters by the year 2100. This shift threatens millions of people globally. The difference between stabilization and these projections relies heavily on our ability to address anthropogenic climate forcing. Climate science works to distinguish between natural background noise and the human-induced signal of global warming. Natural cycles provide the historical context, but they fail to explain the rapid changes observed today. Natural variables like solar output act as background noise. Since the mid-20th century, solar irradiance has trended downward or remained stable, while temperatures have soared, revealing no correlation. The anthropogenic signal is clearly identified in climate models. When human activities are factored in, predictions align perfectly with actual observations, whereas models using only natural factors fail to match the warming trend. The conclusion is clear. The current climate signal is overwhelmingly caused by anthropogenic activities. The background noise of natural history cannot account for the rapid, non-linear warming we see today. By 2026, climate models present a clear divergence in future scenarios, essentially a fork in the road for global climate trajectory. The first path represents a stabilization scenario, where aggressive emission reductions begin to limit global temperature anomalies. The alternative is the hothouse scenario, a self reinforcing trajectory that continues as long as global efforts fail to curb atmospheric carbon. Models highlight that the choice between these outcomes depends entirely on the efficacy of policy success in the coming decade. Predicting the future requires careful monitoring of climate tipping points. These represent critical thresholds where global systems can shift into a new, potentially irreversible state. To model the future, scientists look deep into the past. By analyzing geological archives, such as ice cores, sediment layers, and tree rings, we can understand how previous carbon spikes influenced global life and chemical cycles. We combine this historical perspective with modern emission models. These projections allow us to estimate the impact of rising CO2 levels on life and climate systems through the next century and beyond. We have explored the complex systems driving Earth's climate, from the rhythmic pace of orbital cycles to the transformative impact of our industrial carbon footprint. Recognizing these drivers is essential. Our climate is no longer governed by natural pace alone, it is dictated by our energy budget. Stabilizing our planet requires active management of this balance to ensure a sustainable path forward.